Okay, the next talk in the session is Weakly-Supervised Learning with Cost-Augmented Contrastive Estimation. And it's going to be presented by Kevin Gimpel.
Okay, thank you, and thanks everyone for coming. This is joint work with Mohit Bansal at TTI Chicago. Okay, so the one-slide overview. I'm going to present a new training objective for weakly supervised structured prediction, which generalizes contrastive estimation, or CE, from Smith and Eisner 2005. And it does so by including two new types of what we're calling cost functions. One that looks at inputs, so think of sentences, and one that looks at outputs, so for example, part of speech tag sequences. We need weights for these new cost functions, so that gets us into the realm of doing unsupervised model selection or tuning of those weights. And so I'm not going to talk about this in the talk, but see the paper for our work on the unsupervised model selection. The upside is that we have a better way to do system combination when we're doing unsupervised part-of-speech tagging, where we're able to align the tags across runs. And so the sum of these is an improvement over CE of about 2.5 points in many-to-one and 4.5 in one-to-one. This is an average over 5 languages for the Pascal 2012 shared task. And so we also can improve over the best single system from that task, which was the Grasse et al. Posterior regularization system. Okay, so that's the overview, and now we're gonna dive in. So first I want to talk about some background about EM and contrastive estimation, and then we'll get into talking about these two ways in which we generalize it with different kinds of cost functions. Okay. So the model family we're considering are generative log linear models, so models over pairs X and Y. X is the input, say a sentence. Y is the output, so for this talk, a part of speech tag sequence for X. And so this is globally normalized over all possible X's and all Y's for those X's. And so we're going to assume a standard log linear parameterization where we have a weight vector theta, a feature vector f. For this talk, we don't really need to worry about the internals of that score function, so we're just going to assume a linear scoring function of x and y with weights theta. Okay, and so we're going to consider unsupervised learning algorithms that take this form, where we're trying to maximize a gain function that sums over a set of observations xi. Certainly not all unsupervised learning algorithms can be written in this way, namely Bayesian methods are often trying to do something different, but EM and CE can. And so we're just going to consider different gain functions that fit into this learning framework. So the gain function for EM is simply the log marginal likelihood. So given a sample xi, we sum out all values for the output y. And so for our model, this has this form where we have these two terms. The first, we're trying to increase the score of all y's for the observed xi. And the second, we're trying to penalize all y's for all x's. And I'm writing in this way for reasons that will become clear for comparison to the other training criterion. So CE from Smith and Eisner 05, its gain function is the conditional probability of xi given a corruption neighborhood of xi. And again, we marginalize out all y's. So you can think of this as a log marginal conditional likelihood of xi given its neighborhood. And so for our model, it has this form where the first term is the same as EM. We're trying to increase the score of all y's for the observed x. But the second term differs only in that rather than summing over all possible x's, we're only summing over those in the corruption neighborhood. So this generalizes EM because if we set the neighborhood to be the entire set of all possible x's, we get back EM. So in practice, you choose something smaller for the corruption neighborhood, something for your task or for your data set. And with a well-chosen neighborhood, CE has been found to work well for several tasks. So here's an example of one neighborhood. So this is the transpose 1 neighborhood from Smith and Eisner 2005. So the original sentence is red leaves don't hide blue jays. And then here is its neighborhood represented as a lattice. So the neighborhood always has to include the original sentence. So that's the first path going along the top. And then each other sequence in this lattice is a sentence that results from transposing one pair of consecutive words. So the first one going down is leaves red, don't hide blue jays. And we'll come back to this neighborhood later. And we choose to represent it as a lattice or a finite state machine so that we can do this sum faster. Because we have to sum over all these sequences, and then for each one, sum over all part of speech tag sequences for them during learning. Okay, so that's all I wanted to say about background. Now we're going to talk about the two ways that we modify the CE gain function to inject more knowledge. So here's the gain function for CE again. And the first thing that we note is that all of the sentences in the neighborhood are being treated equally. There's no prior weight that helps us to decide how bad one corruption is compared to another. And so if we go back to our example, the transpose 1 neighborhood, well, we always have to have the neighborhood contain the original sentence. And so this is to make the conditional probability well-formed that we're optimizing. But we would probably like to treat this differently from the actual corrupted sentences. So that's the first kind of intuition we're trying to capture. And the second is that some corruptions are probably not as bad as others. So the first one on the left, leaves red, don't hide blue jays, maybe that's not really as catastrophic a corruption as the other one I'm pointing to, which is red leaves don't blue hide jays. So that's really kind of mucking with the verb, and then blue jays has become changed, whereas leaves red is maybe kind of a more poetic way to write the same basic meaning. So we'd like to change the way that we weight these different elements of the corruption neighborhood. And so the way that we're going to do that is by including what we're calling an input cost function. So it's a function that looks at two inputs, x and x prime, and it returns the difference between them, basically. And we have a weight for that function we'll call alpha that we'll have to tune somehow, and we add this cost function to the second term, so when we're summing over the entries in the neighborhood. And as you'll notice, we can of course pull out delta since it doesn't depend on y prime, and we can have the sum over x prime in the neighborhood and have a weight for that x prime that is proportional to the exponentiated delta. I'm writing it like this to expose the connection to structured large margin learning, and especially the margin rescaled structured hinge loss first developed by Tasker et al. So for this slide, we're doing supervised learning, and so we have xi and yi. So it's a given sentence and its actual, say, part of speech tag sequence. And we're trying to, so this is written as a gain function. We're trying to improve the score of the observed pair, xi, yi, and penalize the score of the so-called loss-augmented y, which has high score and high cost. Below I've shown the softmax version where we replace max with log sum x, because this version is closer to our formulation for CE. But the idea is the same in that, so the cost function here will boost the effective score of the output y. And so during learning, the learning algorithm will pay extra attention to those y's that have high cost. And it'll push down their weights for their features more than the others. And so the main difference, though, is that for the supervised large margin setting, the cost function looks at two outputs, two part of speech tag sequences, yi and y. Whereas for our talk, since we don't have outputs, we're doing unsupervised learning, the cost function looks at two inputs. Okay. So now I'll talk about the input cost functions delta that we will consider in the experiment. So they're both very simple. The first one we call match just goes through the sentence x and counts how many bigrams are in the corrupted sentence that were not in the original. The second one, match LM, is just like match. It counts how many new bigrams we have, except it weights them by the negative log probability under a bigram language model of the second word given the first. And so if we think about this, this is kind of like saying if we've seen the bigram in the observation, and then the second word given the first is not at all surprising, because then the indicator would be 0. But if we haven't seen the bigram, then we want to only penalize it if it's a very surprising bigram. And so if we haven't seen any of them, this ends up being just the log probability of the sentence. Actually, the negative log probability of the sentence under a bigram model. Okay, so before I get into the second kind of cost function, I want to give some results so that we still know what we're talking about here. So our setting is unsupervised part-of-speech tagging. We use 12 tags, so they're just numbers 1 through 12. So we're not using any tag dictionaries. So to evaluate, we're using standard many-to-one and one-to-one accuracy metrics. We're using 5 languages from the Pascal 2012 shared task. And all the numbers I'll report are averages for these metrics across the 5 languages. And you can, of course, see the paper for the results for each language. For neighborhoods, we're using transpose 1 that I showed you some examples of. And we're also using a novel but trivial neighborhood calling shuffle 10, which is just the original sentence plus 10 random permutations. We use standard features from prior work. The only slightly novel features are tag cluster features. So we run Brown clustering on our part-of-speech unlabeled training data twice, and then have features that pair tags in our system, which are just numbers from 1 through 12, with each of the Brown clusters. We optimize using LBFGS. We did, for all of our runs, untuned coefficient strength, L2 regularization, and we found in subsequent experiments that the strength of the L2 term didn't really matter all that much as long as it was small enough. Okay, so here I'm showing results for 2 neighborhoods on the left and both of our metrics on the top. And currently, I'm just showing the contrastive estimation baseline results with no cost function. And this is, again, average over 5 languages. When we add the simple match cost function that just counts how many corruptions there were, we see gains in all 4 settings, bigger gains for the shuffle 10 neighborhood, perhaps because that has more variability in terms of number of corruptions compared to transpose 1. And we see typically further gains when we use the match LM cost. So this is the one that weights the corruptions by basically how surprising they are. And we especially see gains in one-to-one accuracy. Where we're getting about 2.7 points above the transpose 1 number. Okay. So now to move on to the second kind of cost function that looks at outputs. So if we go back to our contrastive estimation gain function, we note that in both of these terms, we're summing over all y's for any x that we consider, whether it's the observed x or one in the corruption neighborhood. And so the only way that we're getting in any information about y is via features. But the feature weights get learned, and so there's no way to inject a specific bias into what we would like y to look like. What kinds of part-of-speech tag sequences do we actually want to get? So now we're going to introduce a cost function that helps us to encode our prior beliefs about y. So we're going to add an output cost function. I'm calling it pi of y, so you can think of it like a prior on y. We're going to include it in both terms, and it has a weight beta. It only looks at y, not x, so this can express preferences on y and doesn't care about the sentence. And this is similar to lots of successful work in weakly-supervised learning in terms of adding structural bias and so on and so forth. So this can be seen as a way of getting these same ideas, which have been shown to work well, but in a declarative contrastive estimation framework. And so the particular formulation that we're using is inspired by this kind of interesting observation that even when we're doing supervised learning, there are some widely used loss functions that don't require us to ever compute the score function for the true output yi. So for example, ramp loss, here shown as a gain function, unlike, say, hinge loss, in ramp, you never have to compute the score of xi, yi. The only place that yi is used is in the cost function. And ramp loss actually has a number of nice properties, which is kind of surprising given how strange it looks, frankly. I mean, to me, it's a very strange loss function. You're trying to improve the score of your model's current prediction, because you're doing the max of the scoring function of y, and then you're trying to still decrease the score of the so-called loss-augmented prediction, just like hinge loss. So we're going to use this same idea. So since the cost function doesn't look at yi, we're doing unsupervised learning where we don't even have yi. This is a nice fit. And in particular, we're going to use a version of ramp loss that I called soft ramp loss 3 in my thesis. There was a number of variations. This one tended to work the best for supervised learning. And so I changed max to soft max and have the cost in both terms. And so to get from there to the CE gain function for this talk, we do two things. So we drop the true y from the cost function since we don't have it, and we have a weight beta for it. And for the denominator, we use the contrastive neighborhood as a standard in CE. Okay, so in this talk, we're just going to consider one simple kind of output cost function. And so we wanted to capture the notion of having some sort of universal tag preferences. So we took some tree banks for languages that we didn't use in our tagging experiments, and we counted their tags and used a simple function based on these counts. So noun is the most common tag in these tree banks. That has cost 0. More rare tags like numeral and particle have higher cost. We did the same thing for tag bigrams. So noun punctuation was the most common tag bigram in our tree banks, and then I'm also showing much more rare tag bigrams here. And so this is where the weak supervision comes in. I think that in practice, if you were going to do unsupervised part-of-speech tagging, you would do so for a language for which you, of course, didn't have any tree banks, but you would like to leverage tree banks for languages for which we do have them. So that's what we're trying to basically replicate with this cost function. Okay, so now some results. Here are some baselines. So now I'll compare it to more baselines on this task. These are two HMM baselines that I trained. One trained with EM and one with stepwise EM. These are two baselines from the shared task, two hard clustering algorithms, Brown clustering, and the make class tool, which work better generally than the HMM algorithms. The best system from the shared task that used 12 tags. So I should mention, we're always using the same number of tags for all these runs, namely 12, because that's the best way to compare these metrics. Generally, having smaller tags gives you better one-to-one. Having more tags gives you better many-to-one. And so it's not so meaningful to compare numbers across numbers of tags. So we're going to stick to 12 tags. But this best system from the shared task from Grassa et al. Did also have the best average one-to-one accuracy across all systems. So when we just run a contrastive estimation baseline, we improve a little bit over the best number from the shared task in many-to-one, though we're about 3 points behind in one-to-one. So we'll compare to these last two rows for the remaining results. Okay, so I've shown those at the top, and then this is the number that I showed you a few slides ago, our best result from the input cost function, namely match LM for transpose 1, which improves over CE by about 1 point in many-to-one and about 2.7 in one-to-one. When we use the output cost function with the universal tag counts, we see slight drop compared to the CE baseline, but a larger improvement in one-to-one, which I think makes sense because with the universal tag counts are trying to do is to better match up our 12 tags in our system to the actual set of tags as you would find them in a tree bank. So it's nice to see that we're getting better one-to-one accuracy there. And then when we combine these two, it's very natural to have a new gain function that has both types of cost functions in it. We see larger gains for both many-to-one and one-to-one. So up to about 2.5 and many-to-one, 4.5 and one-to-one, and also doing better than the best result from the task. Okay, thanks.
Thanks for a very good talk. I was interested in, you sort of had a few things going on. You were copying the contrastive estimation idea of having a limited search space over the space of possible x's using this transpose neighborhood and permutation neighborhood. Had you considered looking at the entire space of x, say through sampling, much like they do in noise contrastive estimation, while keeping your other sort of linguistic biases that you include through your binary LM features and so on?
Yeah, I think that's a great idea. I think one of the motivations for this was to try to reduce the dependency on the neighborhood choice and to just be able to have a cost function so that you can maybe have the entire neighborhood, the entire set of x's like you were saying, and just have the cost function to better discriminate among it. And I haven't tried that. I guess one issue there is that once you start to move into a different algorithm for inference, and now you're doing sampling rather than summing, there might be other factors that may affect things. But yeah, there are probably ways to control for that. And also I guess you have to worry about cost and sort of how long do you sample for. And but as long as you're getting an unbiased sample of the space, and then you could probably test out at least to compare, see how well that would work.
Yeah, I can imagine with stochastic gradient methods, you'll be able to still approach a good solution in the end.
Yeah, that's a good point. Yeah, so you can just maybe sample a handful each time that are different.
Yeah.
Hi. Do you know how sensible is your model to the hyperparameters, like for example, the regularization coefficient?
Yeah, so for the regularization, it doesn't seem to be very sensitive as long as we're using LBFGS and using the same random starting point. Changing regularization doesn't really change much. We do see a stronger effect by changing the alpha and beta, so the weights on the cost functions. So that's why it was important for us to do the unsupervised tuning of those. So I didn't really talk much about that, but in the paper we give a couple of ways of tuning alpha and beta by looking at some unsupervised criterion on held out data. And so yeah, this tended to be important, but we did see fairly consistent curves in the performance across like ranges of values. So it didn't really jump up and down. It was fairly clear that things would peak and then get worse when you have alpha or beta too big or too small. What seemed to be most reliable was since we have to run this for maybe 5 or 6 alpha and beta values anyway, it works better just to do voting. So we just vote with our different models' predictions. And so in the paper there's some info about this better way of voting where we basically do some weighted bipartite matching to figure out how to align tags across different runs. And then once we can do that alignment, we can do very simple naive voting of the tags, and we generally get much lower variance across runs and better performance. But yeah, so things are still fairly sensitive, I would say, to the weights on these cost functions, which is why we spend so much time in the paper at least talking about different ways of tuning them.
Okay, let's thank the speaker.